So, we will continue with this variation length curve. So, it is called VL curve, and there are two types of variance length curve. It's one is called between length, which is called BL, another is within length, is denoted as VL curve. So, VL curve, and as the yarn cut length increases, the between length reduces. On the other hand, as the cut length increases, the variance within length increases. So, effectively the total variance is the summation of between length and within length. Okay. Now, we will see one practical numerical. The problem is here, the nature of BL curve is given, it is a logarithmic curve. Okay. So, which is mx plus c, where y is the variance, that is square of c% and x is the log of cut length. Now, here although this is the shape of the curve, now we can form curve where y axis is in log. If we have the logarithmic value, then the curve will be typically it is a straight line curve. So, many manufacturer they have programmed it is in the logarithmic value, not in this form, but in the logarithmic value which gives the straight line. So, BL curve is normally in the log form. Okay. So, here it is a straight line with the x axis log of cut length and y axis is the variance. Okay. And the variance with 10 centimeter cut length and 1 meter cut length are 49 and 36 respectively, that is given. Now, with this variance, okay, now the thing is that what is the actual problem? It is very practical problem here. Now, we know that this is the BL curve, it is a length, cut length. But if we take the cut length in logarithmic form, normally we get the printout in the logarithmic form, and BL. So, this curve will be like this. Okay. This is the curve, and in the instrument they give this type of printout, not this type of printout, this is the printout. Now, looking at this, here the problem is that at certain cut length, so at 10 centimeter cut length, here the BL value, so 10 centimeter cut length, so BL value is say here it is given 49. So, this is 49, and at say 1 meter cut length, here it is a 10 centimeter and this is say 1 meter cut length, the BL is 36. Now, looking at this curve, 2 points are given, can we predict the value of u%? So, we have these two data only, we have the nature of curve. Now, can we predict what will be the u% of this yarn? That is the problem. Okay. That is our problem here. Now, respect to what will be the approximate u percent of the yarn when it is tested in evenness tester. Now, from VL curve we can try to predict the approximate u percent. Now, this is the BL curve, and from BL curve the variance equal to m log 10 cart length, okay, plus C, that is the equation it is given, and V is nothing but CV percent. Okay. From given conditions, the 49 is the variance m with a cart length of 10 centimeter plus C. So, m plus C log 10 is 1. So, m plus C equal to 49, and for 1 meter cart length, 1 meter means 100 centimeter, 36 m log 100 plus 6 equal to 2 m plus C. From these two equations we can measure the, we can get the value m and C. So, by solving this equation, m equal to minus 13 and C is 62. Now, problem is that we have to see the evenness tester. As we have already mentioned in last class, in evenness tester the u percentage is given where the cart length is 1 centimeter. So, can we measure the variance for 1 centimeter cart length? Yes, we know the equation. So, this is the an Euster evenness tester, cart length is 1 centimeter, approximately we want to calculate. So, V equal to CV percent equal to m log 1 plus C is 62. So, log 1 means 0. So, it is becoming 0. So, it will be 62. So, CV percent, CV square is 62. We can calculate the CV percent, it is a under root 62, the 7.687% is the CV percent with the cart length 1 centimeter. And if we want to know the u percent, then it will be CV percent by 1.25. So, the yarn will have approximate u percent 6.23%. So, from VL curve, from VL curve we can actually predict the value of Euster percent. Okay. So, we can get the 2 points and from there we can always calculate. Okay. Another way of expression of variability is called deviation rate. Deviation rate, it is nothing but it indicates the ratio of total length of yarn irregularity. This is the definition. It is a ratio of total length of yarn irregularity, that means this is the yarn irregularity plot, okay, mass per unit. Now, here we have certain reference length, like what we tell the dr percent of 50% and more. So, this is the yarn. So, this is the mass per unit length which is 50% more 50% or more than the mean mass per unit length. This line has been plotted. We can have different range. So, 75% we can have or 30% we can have. These dotted lines are say 50% plus 50%. So, more than 50%, what is the total length of the yarn? This length, this T1 length is the length of the yarn which is more than 50% of the that length of yarn which is having 50% or more mass per unit area, mass per unit length. This length and here d2 length, this length having the mass which is plus 50% or more, d3 length, d4 length, this is the actual length of the yarn, where it is actually the mass is more. Now, physically if we see, suppose this is the mass, mean plus minus plus 50% and above. This length is mean plus minus plus 50% and above. So, this length is actually measured, this is d1. Another portion here, this length d2, this length is having mass plus 50%. In this way, we will keep on adding d1 plus d2 plus d3, only those lengths portion of yarn, length of those portions of yarn where the mass per unit length is more than 50%. This we have added, then it is divided by the total length of the yarn tested. So, this gives an unique idea of the physically what will be the defect, how the defect will look like. Okay. So, this is one parameter determined on the basis of the yarn irregularity signal averaged over certain length, small reference length, which exceeds the preset length. We have to set the preset. Suppose I want stricter norms. So, instead of 50%, we may call it at 40%. What is the effect, or maybe 60%, at different level we can calculate, and it is on the total length of yarn tested. So, dr percent, it shows the correlation with the evaluation by naked eye. So, it shows the actually the appearance from this value dr percent. Higher dr percent means the yarn actually look total, that total unevenness looking will be there, actual appearance of the fabric will be patchy fabric. Okay. So, that it gives idea, dr percent will give idea the type of look the fabric will give. The other like your u percent will not give this idea, which u percent will only give the okay, this fabric will be having inferior look, but this dr percent will give the total idea of the thick portion which will come up in the appearance. Now, we will see another way of measurement of unevenness. It is a photoelectric method. When a beam of light is directed onto a photoelectric cell, an electric current is produced. Okay. That is the technique we have seen earlier also for other type of measurement. The magnitude of the current is proportional to the intensity of light falling on it, and if the path of the light is cut off by the yarn roving or sliver, the current flow will vary depending on the thickness or diameter of the yarn. So, it does not measure the mass variation, it measures the diameter variation. So, this is the technique here. Here this is the light source, lens arrangement is there, this is the slot is there and yarn is passing through this, and depending on the diameter of the yarn, the light will pass through this, and it is in the photoelectric cell. This will detect the amount of light which is proportional to the diameter of yarn, and as the yarn moves, this will record the variation in diameter. So, we can see here by this animation. So, light is moving through and it is without any material. So, this is there is no material, it is there. Now, its material is there, the material is flowing, that is moving, okay. Yarn is moving, and then light is falling on it. Okay. Photoelectric sensor will sense the amount of light which is proportional to the diameter of the yarn. As yarn moves, the diameter varies at different location, different position, and so it is showing the current variation, and that will get that we can actually plot this variation which is proportional to the variation in yarn diameter. Okay. So, this is the type of plot we can get, this is the plot we can get. So, this is showing the variation in diameter, and then we can calculate the variability. Next is that another optical method which is infrared method, Zuegel's G580 model, which is actually it is optical method of determining the yarn diameter and its variation, and the instrument consists of two IR transmitter of identical in nature and identical receivers will be there, and one of through one the ray, okay, the yarn will pass, it will be blocked partially, and it will be compared with the reference receptor. This is the here the same infrared light of same intensity is passing through, two receivers are there. In one receiver, this is the reference receiver and this is the actual receiver, it is giving I 1 the actual the intensity of light it is getting, here I 2, and the I 2 value is less than I 1 because it is partially it is blocked by the yarn, and the difference will show the actual yarn's diameter variation. So, this is the simple technique here. The same intensity light, two light beams are going, one is yarn is blocking here, now yarn is moving and it is the moving yarn depending on the diameter variation it is giving the plot. Okay. So, intensity of this beam is compared with that measured by the reference receiver, and difference in intensity is measured, it is a measure of yarn diameter. Okay. And that the optical method is claimed to be nearer to human eye in the way it sees the fault, okay, and capacitance method it feels the fault. So, that is how we have discussed earlier that the positive and negative points of the of these two methods. Here it is claimed that this value here whatever evenness value we are getting, it is directly reflecting the actual appearance of the cloth. Next is that the Young fault classification. Although the principle is same as that we have seen the R capacitance type of method, but here we do not measure the thick, thin or nappes. Thick, thin nappes are actually inherent nature, inherent characteristics of yarn. This thick, thin nappes we cannot eliminate, we cannot take out from the yarn, because those are very frequently occurring. We cannot, we can only try to minimize those faults, but there are another type of faults which are in larger dimension, where these faults are not due to the inherent nature of the material or inherent problem in the machine setting or other things, but these are due to some external, mainly due to some external reason, for some, but due to some major machine faults. Okay. This can is, these are not at all acceptable, at least some major faults we have to remove. These are called objectionable fault. The yarn imperfections which have greater than the size, more than 100% of the mass and longer in length, or both, are called as classified as the faults, but the imperfections are less than that, okay, and the lengthwise imperfections are smaller. Okay. Imperfections are more frequent, while faults are seldom events. Faults have greater impact on performance of yarn or appearance of yarn. Faults are classified in different groups, okay. Like imperfections we classify thick, thin, nappes, even thick or different percent. So, here also it classifies at different group, but in fault we, along with the diameter or mass per unit length, we classify in terms of length of the fault. Okay. Based on the requirement of some of them can be removed in the winding operation, okay, by using clearer. So, there are different models, different manufacturers are there of this type of classifier. So, Worcester Classimate 2, which is older version, it has got 23 categories of fault. These are the categories starting from A1 to D4, these are called thick faults. Okay. These are called thick or slab. A, B, C, D, okay. These are basically, this shows the length of the fault, okay, like 1 centimeter, 2 centimeter, 3 centimeter, 8, like these are the length of the faults, and labels 1, 2, 3, 4 are the diameter or mass per percentage, the mass per unit length. Okay. The like A1 means the fault which is having 1 up to 1 centimeter length and plus 100%, that means 2 times of the mean mass per unit length, whereas A4 means the thickest among A group, that means any length up to 1 centimeter and its mass per unit length is plus 400%, that means almost it is 5 times of the mass. So, it is a very thick fault. Okay. Similarly, if we go right way B, C, D, the length will be increased. So, D4 means the length is up to 8 centimeter and that is that long 8 centimeter long and diameter is, so the mass per unit length is 5 times of the average. So, this and E is called long slab. Okay. Here the length is between 8 to say 8 and above, this is the length. So, very long slab, this is highly objectionable fault, and short thin faults are like F1, F and G are the thick fault, but they are not that thick in terms of mass per unit length, but they are long thick faults. These are F and G are long thick fault, and H1, I1 are long thin faults, and H2, I2 are long thin faults, but the diameter or mass per unit length is much less. So, if we see the severity of fault is E is the actually it is a very thick fault, and I2 is very thin fault. If we see if we tell the which, the question if we ask which fault is responsible for breakage in subsequent process, this will be definitely I2 H2, this will be maximum, this will be the reason for the breakage. Which fault is responsible for very high slab appearance, E fault or D fault or C fault. So, if we see the objectionable faults are either very thick or very long faults. These are objectionable fault, and we can identify this A4, B4, C3, C4, D3, D4, these are actually objectionable faults, because these are either thick or these are longer faults. E is always objectionable. Okay. So, A4, B4, C3, C4, D3, D4 they are objectionable faults, and if we try to have some stricter norms, if we want to have better quality yarn, and these faults can be removed in the winding process, and here we have to also see the number of breakage in the winding, because one break means we are introducing one fault also, we have to splice. So, if we want to have stricter norm, then in that case A3, B3, C2, D2 can be A3, B3, C2 and D2 can also be considered objectionable fault. So, these are the you can add. So, we can keep on adding the fault, if we even if we can think the A2, B2 we can add, that we can do, but at the same time we have to consider the efficiency in the winding, because the number of faults are increasing, these are in cumulative form. So, A4 number of A4 faults are much less than A3, and A3 is much less than A1. So, A1, A2 they are large number. Okay. So, if we consider to remove A2 even, then the number of stoppage of the particular working head will be very high, and number of cut, number of splice will be very high, that will affect actually indirectly adversely, that will affect the quality. Okay. So, that is why we have to decide what type of faults we have to remove. We may think okay, we will work with B4, C4, D4, D3, then it is fine. So, in that case number of stoppage will be less, and the H1, H2 we can. So, I1, I2 we can see which one we can remove. So, long thick faults E and G are objectionable. So, these are objectionable, we can always remove. So, E we cannot always have, we can always we have to remove these faults, and thin faults H1, H2, I1, I2, H2, I1, I2 these are objectionable faults, these are more critical because they cause breakage during further processes. Okay. they also show up in thin lines in this fabric. So, we have to remove these faults. The objectionable faults are cleared by Yann clearer. So, Yann clearer is set, and there are some settings we can set the what type of faults we want to clean. Okay. And Classymate 3 next model, which is actually where instead of 23 types categories, they have actually classified in 33 categories. That we can always do. This is only matter of software. Okay. We can always classify in more and more, because we have data. Once we are getting data in the from the capacitance type sensor, we can always do. Like another tester which is called Kiyosaki Classifault. There it classifies 40 different categories. So, it is simply simply the software, we can keep on adding the variability, okay, different levels. The basic principle is same. So, another instrument which is electronic inspection board. So, where it sense it measure in Lawson-Hampel instrument, where it actually works in photoelectric principle and objective method of grading the Yann appearance. It stores the data, Yann diameter data, and automatically form the Yann board without, as we have seen the Yann board wrapping, it will automatically form the Yann board and it will compare with the standard. So, we do not have to do anything. Yann is run and scanned between the light source and the camera at a rate of 2 scans per millimeter when running at the speed of 100 meter per minute. So, information from the camera is digitized and transmitted to the computer. Yann profile program produces a profile image of the Yann as well as the graph of variation of the diameter. So, this profile program is there and inspection board program is there, the two types of programs one can have. So, automatically it will form a Yann board and it will automatically be graded Yann appearance board. So, we do not have to do anything with the standard grade. So, after that we will just try to finish quickly. So, we can also measure the evenness or faults online. So, whatever things we have discussed or basically these were actually the offline techniques. We have to take the yarn or material from the machine and test offline, but there are techniques like in Slaforst, the Corolab, the rotor spinning machine, they have fitted the optical sensor with each and every end, each and every rotor actually rotor box, okay, and measure the variability of yarn online, and immediately it gets signal in the central processor and detects the fault online, okay, and identify the which machine is producing the problem. Earlier methods what we have done, it was basically it is a post-mortem. We already yarns have been produced, we are getting the values and try to rectify for next process. But this type of online process is actually it is very useful, so that we can get online immediate, we can rectify the problem. Worcester Polyguard is also there, which works on the capacitance principle and it gives the information on variability. So, with this we have come to the end of the session evenness. Okay. In next session we will discuss the other parameters other parameters means we have all completed the fiber, we have completed fabric, yarn, and now we will see few test methods, few testing techniques for fabric. Okay. Till then, goodbye, thank you.